Here we're going to look at example 8 from the chapter on mechanical systems. Please note that this example does not appear in the pre-printed notes, but you'll need to download a copy of the problem that appears as a PDF link on the lectures page of the blog. What we have here is a spring mass dashpot system, one mass with 3 springs and 3 dashpots. We have springs K1 and K2 on the left side in series, dashpots C1 and C2 in series there on the left side. On the right side we have K3 and C3 for the spring and dashpot. What we want to do is come up with the equation of motion for the system in terms of x, where x is measured positively to the right. First step I'm going to go through here is to replace these 2 springs in series by a single spring on the left hand side. So that force is going to be a K equilibrium times x. When x is plus, the arrow goes like that. What is K equilibrium? Well, recall that for a series connection like that for the springs, we have 1 over K equivalent is equal to 1 over K1 plus 1 over K2. Springs in series, the inverses add together to give the inverse of K equivalent. What we need here is K equivalent. So the right hand side will put that over a common denominator here, which will give us a K1 plus K2 divided by K1 times K2. In other words, when I solve for K equivalent, I get the product of the 2 divided by the sum of the 2. In the same way, I'm going to replace these 2 dashpots in series by a single dashpot of damping coefficient of C equivalent. So that force is a C equivalent x dot. It's acting to the left. And in the same way, I won't go through this again, but you'll find that C equivalent is equal to C1 times C2, the product of the 2, divided by the sum. So that's what we've got. The spring here on the right, we'll treat that in the regular way. If I write this as K3x, x here is the deformation of that spring. The right side is fixed. When x is plus, the spring is compressed, so it's going to push to the left. We have the C3x dot. When the block is moving to the right, when x dot is plus, it's being resisted in that motion by the dashpot, so the dashpot is pushing like that. So we have our FBD written in terms of the equivalent spring constants and equivalent dashpots like that. For step 2, our Newton. If I sum forces in x, get minus K equivalent minus C equivalent times x dot. Got a minus K3x minus C3x dot like that. And that's equal to the mass times the acceleration x double dot. And that's it. We bring all of our terms together on one side. Mx double dot plus C equivalent plus C3 x dot, K equivalent plus K3 times x is a 0. That is our differential equation that describes the system, which is made up of the 3 springs and 3 dashpots. So the key parts here are this. 1, replacing the 2 springs in series by a single spring of stiffness K equivalent. and then replacing our two dash pots in series by an equivalent dash pot of damping coefficient of CEQ. So that was a crucial first step. And then the second part just falls in just like everything else we have done. But when we get through, we see that the equivalent spring here on the left-hand side is in parallel with the spring there on the right. The equivalent dash pot here on the left is in parallel with the dash pot of damping coefficient of C3 there on the right side, because they add together. These add and those add. So this last part was more of an observation of a result, where the first part we directly replaced the series springs and the series dash pots by their equivalent stiffness in damping.